What's, okay, where are you hung up at? Do you know where we get these numbers?
Yeah.
Okay, and we understand that that equals 100 because we're adding everything across?
Yeah.
Yeah, okay, cool. Do you know why we have these numbers?
Yes.
Why?
Because it's like 25% of
Well-
I mean, 75.
So, why 75 and 25?
Because we expected that.
So, we said tongue rolling was a dominant trait, right? So, if you have this, it doesn't matter what this is, you can roll your tongue, correct? And we said that everybody's parents that we looked at were hybrid or heterozygous. So that means everybody that we looked at, their parents were like this, genetically, right? So if we do that cross, that's a tongue roller, that's a tongue roller, that's a tongue roller, that is not. So 75% of the offspring we could expect would roll their tongue, and 25% not. Right on? That's what that expected is. We expected, because we had 100 people, let's say we had a population of 200 people. How many would we expect to be able to roll their tongue? Well, you would just take the total number that we have, and we expect 75%. So 75% of 200 is 150, right? So we take that percentage and look at, okay, out of the total population, we expect 75%. So whatever number you're given for observed, this would still be 75% in this instance. So that's where we get these values. Are we cool with that? Okay. Observed minus expected. So we just basically take this, 90 minus 75. 10 minus 25. You will get a negative number. This is why we square it, so that all the numbers are positive. That's the only reason we square it, so that we don't have to mess with negative numbers. Cool? And so squaring 15 and negative 15, we get 225. Observed minus expected squared, which is just this number here. We don't have to do the math again, right? We're breaking it down into steps. So we're like, okay, put a number here, take this number minus this number. So this number minus this number. Then this minus this number minus this number is right here. Square that. That's the only step. We're going step by step by step. And after you square it, then divide it by what was expected. Right? Just break it down step by step by step.
That's pretty simple for smart.
If you do it the way I have it here, if you label these columns, column A, B, C, D, and E. If you think about the columns this way, right? And let's just do it like this. So, observed, we had 90, 10, expected, 75, 25. So this was 90 minus 75, this was 10 minus 25. So this was 15 squared, negative 15 squared, right? Equals 225, 225. This was 3, and this was 9. So the sum equals 12. So if you write it out this way, these are the steps. Step number 1 is A minus B. You have to do observed minus expected. 2. The answer that you got in step 1, so step 1, so square step 1, which is these two, right? Number 3 is, divide step 2, or you could just do step 2 divided by column B. Right, so this here divided by column B, 4, is you add them all up. That's it, that's all we're doing. You will be given on your exam all the math formulas you will need. On there will be this table. It's called a chi-square table. This is where you look up your critical value. Degrees of freedom. Degrees of freedom are the choices or results you could have received minus 1. In our instance, you could roll your tongue or you could not roll your tongue, right? Those are the two possible outcomes. So if there's two possible outcomes, that's the same thing like flipping a coin, heads or tails. There are two possible outcomes, right? Your degrees of freedom are the possible outcomes minus 1. Does that make sense? What are the degrees of freedom for this problem? 1. Cool. That's these columns here, degrees of freedom 1, 2, 3, 4, 5, all the way through. Right? If we did a dihybrid cross, what are the degrees of freedom? You end up with a 9 to 3 to 3 to 1 ratio, right? That gets a little goofy. We'll get into it. We'll see it one, right? But how do you determine it? The possibilities minus 1. You could roll your tongue or you could not roll your tongue. So those are the two possibilities. Minus 1 is 1. If it were rolling the dice, what would the degrees of freedom be? 5. There are 6 sides to the die. Minus 1 is the degrees of freedom of 5. If it was a coin, it's 1. Right? You cannot have 0 degrees of freedom. Right? You can't have just one outcome. Right? 100% will be this. Well, then there's nothing to test. Right? The P is the probability or our confidence interval. We want to be 95% confident in our data. So we will always use the 0.05 column or row. Always. 0.01 means we're 99% confident in our data. We hardly ever use that. I mean, that's right. But, so determine the degrees of freedom in your experiment. With the chi-square, you must determine the probability that the difference between the observed and expected values occur simply by chance, or you determine if there's something else influencing your data. Your degrees of freedom, again, like I said, is going to be the possibilities minus 1. Compare your calculated value to the appropriate value in degrees of freedom table. So, how many degrees of freedom do we have? 1 degree of freedom, and our value is 0.05. So, what is our critical value? Just look at where those two line up. The P is at the 5, 1 degree of freedom, 3.84. Alright, that's the number that we're going to use. If we're using die, the number would be 11.07 because degrees of freedom are 6, or choices are 6, degrees of freedom are 5,
So we would-
we want the 95% confidence interval, so the number we would compare would be the 11.7.
So we would multiply 3.84.
No, it's not even that tough, dude. All we're just gonna do is look at the numbers, see which one's bigger. So, calculate degrees of freedom, number of categories or possibilities -1. For this problem, there are 2 categories, tongue rollers and non-tongue rollers, right? So the degrees of freedom, 2 minus 1 is 1. That gives us this one right here. So we're all good with this, right? It's fairly simple. This presents our confidence. So 0.05 means you're 95% confident that your observed data fits your expected data. 0.01 means you're 99% confident that your observed data meets your expected data. There's, because we always use the 0.05. General rule of thumb, we always look at the 0.05. We want to be 95% confident in our data. Or 95% confident that what we say about our data is accurate. So all good? So these are critical values. We want to use where they align. So the 0.05 and the 1, this is for us, right? So interpreting the results of the degrees of freedom, if chi-square is greater than your critical value, there's something going on. There's something statistically different between what you observed and what you expected. This means that any difference in the numbers isn't due truly to chance. Because, I mean, nothing is gonna fall 100% into the categories, right? Is it close enough? This is where you sit there and where people can fool you with numbers if you don't know what's going on. When they say 4 out of 5 dentists recommend this toothpaste, you ever stop and think about that? That's only 80%.
So like.
What do the other 20% recommend? Right? 3 out of 5. Right, that's not very good either, that's 60%, right? Right, but it sounds good if you say 3 out of 5, you're like, well, that's more than half. Well, wait, it's only 60%. Right? 4 out of 5 dentists is not as good as 9 out of 10. Right? So this eliminates that kind of thinking, where you can be manipulated with numbers. Right? If we say, oh, 90, that's only 15 off from 75, well, that's close enough, right? 90, 75, doesn't sound too bad. Right? This eliminates bias. This is why we use it. So, if the chi-square is greater than the critical value, you have to reject the null hypothesis. The null hypothesis says any difference in what we observe and what we expect is just by chance. It's close enough, right? We expected 75, we got 82, that's close enough. Right? That's kind of what we're saying. But if the number isn't close enough, you have to reject the null hypothesis. The null hypothesis is always that there is no statistical difference between what we observed and what we expected. If you reject that, you're saying there is a statistical difference between what we observed and what we expected. Something goofy is going on. If the chi-square is less than the critical value, there is not a statistically different observation from what we expected. And you accept the null hypothesis that says, all right, my number isn't exactly 75, but it's close enough. and then you will accept the null hypothesis. These numbers are good enough. I have confidence in what I observed and what I expected.
But Mr. White, if you move, what's gonna happen to your life? You just gonna leave them?
Yeah.
That's mean.
Good. So, in this example that we did, our chi-square, the sum of all that was 12, right? 9 plus 3 is 12.
Yeah.
What we got here. Right on? So our chi-square value is 12. 12 is greater than 3.84. Therefore, there is a statistical difference between what we observed and what we expected to observe. Which means we have to, do we accept or reject the null hypothesis? Reject it. And if you reject the null hypothesis, you're saying the difference in the numbers is not just due to chance. There's another explanation for what is happening. What?
Hey. Hands on the page. Oh, yeah,
Alright, so let's practice. In peas, yellow seeds are dominant over green seeds. In a cross between two plants, both heterozygous for seed color, the following was observed. Does the data fit the predicted phenotypic ratio? What's the first thing you've got to figure out? What's that? Okay. So, let's go here. So we've got yellow and green, right? And we observed 4,400 and 1,624. What do you expect? What did it tell you the parents were? Heterozygous. So we have this. Do I need to do a Punnett square? No. What do we expect? 75%. So 4,400 times 0.75 and 1,624 times 0.25. Right? This is what we expect. What do we have there? all those little calculators, come on. What do we expect? Oh, wait, don't do that, I'm sorry. I wrote the wrong number down. Forward to, we have 6,024. I'm sorry. So out of the total, we expect 75% of that to be this and 25% to be this, right? I'm sorry. Hmm? 6024, because that's our total, right? Population, and we expect 75% of that total population to be that. So we expect 4,518. So here, 4,518, and then 1506. Okay, so observed minus expected. So here we have 4400 minus 4518, and we have 1624 minus 1506. What do we get then? Negative 118. What do we get here? 118. So the square of those, 13,924. And each of those divided by expected, so 13,924 divided by 6024. 2.31. Cool. And 13,924 divided by 1624. 8.57. Cool. Add those up. Hmm. What's 4400 divided by 1624? What is this divided by this? So we'd end up with 10.88, according to my quick math up here. So. It's still within, right? 1624, 6024 divided by 0.7. Oh, that's green. There's yellow. Okay. Why did we end up with these two numbers so far off? 3.08, 9.24, 13,924. How do they have 13,924 divided by 1506? What is, do that again, 13,924 divided by 1506?
Sorry, I did it wrong, my bad, guys.
Is it 3.08? What?
It's 3.08.
13,924 divided by 1506.
It's 9.24. Well, 9.25, because I rounded up. He's doing the yellow. When he just read the equation, he's going to yellow.
They might have. Yeah, the numbers in the bottom of the table are traversed. But they still, regardless whether we add this to this or this to this, we still get this, right? 12.32. 12.32, how many degrees of freedom do we have? One. Is 12.32 larger than 3.84?
Yes.
Yes, so we
Reject.
reject the null hypothesis. So the results are not due to chance. There's something else happening in that situation that is making yellow more dominant than green. We have no idea what it is, we can't say what it is. And now environmental effects on phenotypes. Various environmental factors can influence gene expression and lead to phenotypic plasticity. Plasticity means it'll change. Can you think of any? Can you think of any environmental factors that might change gene expression, change phenotypes? Anything? Anything? What? What? Sure, weather, more specifically, seasons, right? And how so? Can you think of an organism? Yeah. If it's a deciduous tree, it's going to change color of leaf and things like that, right? There's animals also. Hmm? Nobody knows? Yeah, that's, not quite what it is, that's just an adaptation. The one we usually refer to is like the Arctic fox.
Oh, I was thinking.
During the spring and summer, the Arctic fox is a brownish red. At winter,
White.
yep, totally turns white. No, you have white bunnies. So individuals with the same genotype can exhibit different phenotypes when they're experiencing different environments. Temperature can change, coat color, oh, I suppose, yeah, maybe rabbits. Siamese cats, Arctic fox. Soil can affect flower color. UV exposure increased melanin production in the skin. Somebody ran out of 5 bucks. chromosomal inheritance and disorders. Some genetic disorders may link to affected mutated alleles or chromosomal changes. Mutated alleles.
What, I think, can you go back please?
Really? Genetic disorders can be mutations or chromosome changes, that's it. Mutation is just, hey, it's supposed to be this letter and it was this letter instead. That's all. Alright, so Tay-Sachs disease. Oh my gosh, dude. All we're saying is you can have a disorder if your DNA is messed up. That's it. That's all that last line said. Tay-Sachs disease, one allele base change substitution, and you're gonna be dead before you're 5.
What?
Autosomal recessive disease. Okay. Yeah, out of 3 billion base pairs, you change 1 letter, and there is only 1 outcome. As an infant, somewhere between 6 months and a year, they're gonna start noticing that you're not developing the same. You're gonna come out normal. You're gonna miss milestones. You're not gonna sit up. You're not gonna talk. You're not gonna hold your head up right. You're not gonna crawl. Then you're gonna go blind. Then you're gonna have seizures up to 20 times a day, not be able to eat solid foods, and then you're gonna die. Nope. There's no cure, no treatment. It's a waiting game. Your parents are gonna wait around until you die. It's sad. It is a, right? This is horrible.
Is there no way to tell like
No.
all the babies in the womb?
There's no reason to be tested unless
What's the
you,
percentage of babies?
not very high. That's why nobody tests for this.
Like,
If you're an Ashkenazi Jew, which is a very specific region in Europe that Jews live, if you're an Ashkenazi Jew, it is more common in your population, but still, it is so rare in that population, nobody gets checked. It's an autosomal recessive, meaning you have to inherit 2 bad copies of the gene, right? It's super rare. But if it happens, that's it. So, if you find out you're Ashkenazi Jew and your mate is Ashkenazi Jew, you know, either you're 23andMe or whatnot, yeah, I would probably have DNA screening done to see if you carry the Tay-Sachs disorder. Because if you do and your mate does, there's a 25% chance that's going to happen to your offspring, and that may dictate whether you ever elect to have kids or not. Right? Are you willing to take that chance? Tay-Sachs disease is there's an enzyme that is